Good afternoon. David De Los Reyes, my topic for this afternoon is still plane area using polar coordinates. We are now through with the Cartesian coordinate system of solving area, meaning x and y axis. So my discussion for this afternoon will be the computation of plane area using polar coordinates. What is polar coordinates? Polar coordinates, the given equation should be in terms of radius and angle. Polar. Polar meaning angle. Okay? So there should be a constant or variable radius and constant or variable angle. Okay, I will try to bring out the formula and I will show you how it was derived. Okay, let's proceed. Topic number 54 under my channel. Topic integral calculus, plane area. Under the topic again, polar coordinates. We are now through with the Cartesian coordinate system of computing areas. Okay. I will give you the formula, then I will try to give you the derivation, and I will give you an example. For polar coordinates, differential area is 1/2 of r squared differential theta. If the given equation is a polar coordinate equation, meaning in terms of radius and angle, this should be the formula on how to take the differential area of any given function. Okay, r is constant or variable. Theta is variable. Okay, so actually what is given under polar coordinates is r as a function of theta. Okay, I will derive the formula how come the differential area under polar coordinates is 1/2 of r squared differential theta. Okay, I will try to draw a differential area under polar coordinates. This is a radius r. This is an arc. And the angle inside is differential theta. A very minute angle, it's a differential theta. Okay. The figure will be something like this, guys. This is r, and this is also r. The angle inside is differential theta. And here, I place the designation of this side here to be h. I put a perpendicular sign over here. As you see it, guys, it's something like this. So actually, I remove the one with the dotted line. The area with the dotted line is very minute. If the angle is too small, the area under the dotted line is very small. So actually, I could say that if I will try to draw a line from this point here up to this is a very small arch, okay? If I will connect this one, I could designate this as letter h, the height of the resulting triangle. I assume for the meantime it's a right triangle. It's a very minute right triangle. So actually this h here is almost equivalent to the arcs, okay, if this angle is very small, okay? So to compute for the total area, of this, okay, to compute for the total area of that, I will now try to bring out a right triangle, something like this. This is h, this is r, this is r. Actually, the arch is here, okay? But I remove it because it was very small, minute, okay? This is actually the difference, okay? And this is actually differential theta. Discounting this one for the meantime because it is very small. So what will come out from our figure is just, it seems like a right triangle, right? So if we take the total area of this, we know for the area of a right triangle, I will place differential because this is just a small area, differential area. Differential area now will be equal to 1/2 of base times height. The base will be equal to r, and this height here, okay, will be r differential theta. The circumference of the circle is actually 2 pi r. But if we are only taking the certain arcs, okay, the length of a certain arcs, this the length of the certain arcs is just the radius times the angle included at that arcs. And in here, the included angle is differential theta. So the length of this arcs here will be r differential theta. So actually, I could place this h here as r differential theta. You got it, guys? So this will now be equal to 1/2. Base is r. H will be r differential theta. And differential area now for plural coordinates, sorry for that one. R times r is r squared. This should be 1/2 of r squared differential theta. That's the derivation of the formula. Differential area under polar coordinates is 1/2 of r squared differential theta. Oh, you got it, guys? Because the arcs here is too small. So if this is r differential theta, the arcs, if this angle here is, if differential theta is too small, h will be almost equivalent to the arcs, and that is equal to r differential theta. So under polar coordinate system, if you are given r as a function of theta, and they are asking for the area included between two angles on that given function, to solve the area, just use this formula. Differential area is equal to 1/2 of r squared differential theta. Okay, that's the derivation of this. It was derived from the area of a right triangle because if this angle differential theta is too small, the arcs is almost equivalent to this h here. So actually, I place h as r differential theta. Okay? Oh, that's the derivation. Okay? Okay, I will try to give you an example. To observe the significance of this formula, let's try to bring out the derivation of the formula for taking the area of a circle using polar coordinates. So, example problem, derive the area of a circle if the radius of that circle is, if the radius is small letter r. Okay, let's try to draw the figure. Under polar coordinates, this is the 180 and 0 axis. This is the 90 and 270 axis. It seems this is the x-axis. This is the y-axis if we are considering the Cartesian coordinate system. But under polar coordinate system, this is the 180 and 0, 0 and 180, the horizontal line. And the vertical line is the 90 and 270 degree line. Okay? So, if we try to draw the circle, this should be the circle. Okay? The radius is r. Okay? This is r, this is r, this is r, this is r. So, at any angle within the polar coordinate system, the radius is actually constant. This is R, so it's an easy problem. The radius is constant. Okay, I will draw the slice on the polar coordinate area. Okay, this is the differential area. The angle between this differential area with respect to the 0 degree is theta. The angle inside is differential theta. This is R. Okay? So using polar coordinates and by using symmetry, to take the total area of this, we must rotate this differential area from 0 to 90, 90 to 180, 180 to 270, then 270 to 360 for us to complete the area of the circle. I got no one end. Okay? Right? We must rotate this differential area from 0 to 90, 90 to 180, 180 to 270, then 270 to 360, 360 or 0, one complete revolution. Or by using symmetry, you just rotate the differential area from 0 to 90 degrees, then multiply it by 4. Okay? So differential area over 4 will be equal to, we are following this, 1/2 of r squared differential theta. What is theta 1? Theta 1 is the initial limit. It will be 0. Okay, so it's 0. The upper limit will be 90 degrees, or in terms of radians, this will be pi over 2. To take 1/4 of the area, the differential area should rotate from 0 to 90 degrees, or from 0 to pi over 2 radians. Okay? I place the note over here, r is constant. For a circle, the radius is constant. It's not variable, right? So, integrating both sides, the integral of the differential area equal to, okay? There was a 4 here, actually, a 4 a while ago. I place it on the right hand side, so this is gone. The integral of the differential area will be equal to 4. We are following this. I bring out 1/2, it's a constant, right? 1/2. I bring out r squared. Why I brought out r squared? It is also a constant, r squared. The integral from 0 to pi over 2. The only variable thing is the angle, right? It is differential theta. And luckily, the integral of the differential of theta is just equal to theta. Easy money, guys. We passed by the integration of the different integrations. This is an easy thing to do, right? Under application. Therefore, area now will be equal to, this should be 4 over 2 will be 2 r squared. The integral of the differential of theta is just theta. So this will be theta from 0 to pi over 2. Area now will be 2r squared. Upper limit will be pi over 2. Lower limit will be 0. So this is minus 0. What angle we place here, the unit should be radians, okay? So we will convert that 90 degrees to radians, and it is actually pi over 2. Because 2 pi is 360. Okay? We divide this by 4. Okay? These 2 here cancel with this. Pi over 2 now. This will be equal, 360 over 4 is actually 90 degrees. So 90 degrees is pi over 2. So this will now be pi over 2 as upper limit, minus the value of the lower limit minus 0. 0 degrees also 0 radians, so this is minus 0. Or this is just simply times pi over 2. These 2 here cancel with this. So the general equation for taking the area of a circle in terms of radius is area for a circle is pi times the square of the radius, square units. Okay, that's it, guys. Under a polar coordinate system, the derivation is a little bit easy luckily. But for other functions, we should not be unlucky. It might be a complicated problem. But initially, to solve for the differential area, you just follow this. For polar coordinates, differential area is 1/2 of r squared differential theta. And there should be a given relation of r in terms of theta. Okay? There is r, and there is theta. There should be a relation for you to make a graph of that required area. Okay, guys, that's it. That's our topic, plane area under polar coordinates. Our given example is the derivation of the area of a circle in terms of radius. And as a final formula, area is equal to pi r square. Good afternoon, Los Angeles.